It's the Keynote, Reimagining Silicon Chips for a Quantum Future. Our presenter, Andrew Dzurak, the CEO and founder of Diraq, the company, not the man. Please join me in welcoming Andrew. Cheers.
Thanks very much, Bernie, and thanks so much to SQA Quantum Academy for putting together such an amazing conference. It's so great to have so many world leaders here speaking about the future of quantum computing. We've just had a fantastic panel, and that was a great discussion about the challenges of reaching fault tolerance. I'm really so pleased to be able and honoured to be able to talk here today about Diraq, our company. I'll tell you a little bit about the company's plans as we grow and develop, and also why we believe very strongly that silicon CMOS manufacturing is really the pathway to reach the fault tolerance that we've just heard about from the panel, and why we believe that it is the right technology choice to get there. I'll also just want to say that we really believe that being here in Sydney is very, very important for our company. The ecosystem that we have in Sydney, and I should say much more broadly in Australia, right around Australia, the talent that we have here across all levels of the quantum computing stack is really astounding, and it's an important advantage for our company. The other thing I would say is that ultimately quantum computing is a global business, and we've had the opportunity to hear from lots of different companies from around the world throughout this conference. And there's no question that ultimately we must partner internationally. Our markets will ultimately be primarily international, but going to the question of what we can do with manufacturing in Australia, there's a huge amount that can be done here in Australia. Building a quantum computer is a lot more than just making chips. Okay, we heard from a number of the speakers, David Riley and others, and throughout the whole conference, about just how much work needs to be done to build a full quantum computing system. And we've got companies like Q-Control here who are doing amazing work on developing the software and the higher levels of the stack. We've got outstanding quantum algorithm capabilities in a number of places in Australia. UTS's Centre for Quantum Software, for example, being just one example. So there's so much manufacturing to be done at various levels of the stack. Assembling these quantum computing systems, for example, is a serious business, and this can all be done here in Australia. But there's no question that we have to be part of global supply chains. So let's move on. Let me just check that I can control this. A big green arrow, that's probably the one I should press. All right, so we've heard from a couple of speakers about the fact that there are many, many different types of qubits, and in theory, any physical quantum system, two-level system, can encode a 0 or a 1, but there are a number of requirements that we have in order to actually make a useful qubit. We have to obviously read the information, we need to be able to write information on it, we need to be able to couple them, and we need to be able ultimately to perform complex calculations. And so where we are today is that we have a number of different approaches being explored by different companies and research groups. I apologise, I haven't put absolutely every one of them up here. For example, I should have squeezed in neutral atoms. We heard a great talk from cold quanta and inflection the other day. But you know, these ones here, plus perhaps neutral atoms, are really the ones that most of the investment around the world is working on. And forgive me if I haven't included all of the companies and research groups. There's now so many, of course. We've also heard about the levels of investment that's going on, both by big corporations and also from private investments that are building startups, many here in Australia, but all around the world. We heard some great talks about what's going on in the UK, in the US, in Canada, etc., and much more going on in Europe as well. This is now probably, I'm certain, an incomplete listing taken from the website, their Quantum Computing Report. I think they've updated this recently, just showing the number of companies that are now in this space at various levels of the quantum computing stack, also companies that are looking at providing full stack capability, and that certainly includes Diraq. And the motivation for all of that private investment is ultimately the potential market that full-scale, fault-tolerant quantum computing can achieve. So you can see the market analysis. This is from BCG. A couple of years ago, McKinsey and others have also done similar analysis and arriving at similar figures. They are predicting that when we have fault-tolerant quantum computing, the total market will be some very decent fraction of $1 trillion per annum. That is a significant amount of money, and I'm firmly convinced that Australia, across the various companies that we have here, has a great opportunity to tap into a very significant fraction. And we heard from Ed Husick yesterday and Kathy Foley the day before about all of the efforts of the Australian government to try to capture as much of that as possible, and certainly Diraq is very focused on doing that for Australia, but again, as I say, build a company that is a truly global company. So again, lots of talks throughout this conference about the various application areas, okay? We've heard about a whole range of applications, and you can see just some categories listed here: molecular modelling, simulation, optimization problems, routing problems, etc. And the one we heard about yesterday afternoon in some detail was the issue of quantum chemistry, originally inspired by Richard Feynman's observation that if we want to simulate and model computationally a real biological or molecular or chemical system, then we need a quantum computer to do it. It's simply impossible to deal with all those variables, even on the most powerful supercomputers that we could ever build using classical computing. And this particular problem, I must say, is the one that excites me the most in terms of the really profound outcomes that could be achieved for humanity if we can find much faster ways to fight disease, fight viruses. We heard yesterday from a really expert panel, including some outstanding researchers here in Australia, about the challenges, and all around the world, about the challenges of doing quantum chemistry and what is required. And we heard that it is quite a daunting task. We need many millions of qubits to do that, to achieve these sort of problems. And that's just for quantum chemistry. Indeed, really most of those world-changing applications I talked about before will require many millions of qubits. So let me just spend one slide talking a little bit about some of the details of that. And this is taken from a paper from Microsoft Research, led by Matthias Treuer, who was at IBM, who was at ETH Zurich and now based in Redmond in Washington, and with Microsoft. And this was an analysis of what would be required to solve or to look at the nitrogen fixation problem using this molecule FOMOCO. And so they were looking at the resource requirements, and I'm not going to get you to read all of those numbers, but let me just focus on a couple of the key numbers. So on the top line, we have the error rates of different, of the actual physical qubits underlying the quantum system. Okay, so you can see an error there, 10 to the minus 3, which is 0.1% error, which corresponds to a qubit fidelity of 99.9%. We then move to the right to some very, very scary physical fidelity numbers. I'll come back to those in a moment. So for each of those different possible physical qubit fidelities, this particular problem, in order to do a useful calculation, requires 111 logical qubits. And at the bottom line, this is the number I really want you to focus on. These are the number of physical qubits in order to solve that problem with the fidelity, the physical qubit fidelities at the top. Okay, so as you can see, there's some pretty big numbers there. And while I was rereading this paper, I picked out this particular quote in the paper. So it's saying, after doing all of the analysis, we arrive at the conclusion that only 100,000 to 1 million physical qubits are needed if the error rates are 10 to the minus 6 and 10 to the minus 9. Okay? Now, that may sound fine for theorists, but as an experimentalist, and I'm sure for all other experimentalists in this room, you would be waking up in a cold sweat at the thought of having to produce physical qubits with error rates at 10 to the minus 6 or 10 to the minus 9. Okay, so, and it's being found now by pretty much all companies that are starting to scale up qubits, superconducting qubits and others, that as they increase the number of qubits, it's a real challenge to maintain those physical qubit fidelities. So I personally, my personal view, I could be wrong, I've been wrong before, but I pretty strongly believe it's going to be very, very difficult to have very, very large numbers. And remember, even at those fidelities, you still need 100,000 to 1 million qubits, right? So my personal view is that we have to focus on scale. It's all about scaling up and getting as many as we possibly can. And that's really the whole focus of Diraq, to get to large numbers of qubits while maintaining good fidelities, as good as we can. We need to keep pushing on those numbers as well. So where are we at the moment? Well, we've already heard from a number of speakers that today we are still in this NISQ area. Okay, noisy intermediate scale processing, no error correction. And there have been important results. So on the left there, I've listed a few really important papers, and some people in this room have been involved in some of that work. Quantum supremacy has been a very, very important achievement over the past few years. It's shown that a quantum computer can do something that a supercomputer can't do, or at least not for 100,000 years. And that's really important results. But the reality is that to do useful calculations, at the moment, even the most advanced systems in the world are still simulating problems that we can largely do using even a laptop. I know that there is great work going on, and it's important to explore NISQ algorithms and to look at opportunities. And you know, I think that people hope there will be some NISQ algorithms that will genuinely produce some commercial benefit. But as analysed in this BCG report and others, you can see the bar there at the top for the total expected revenue from NISQ capabilities compared to fault tolerance. And given the amount of investment that is really required you know, to make quantum computing possible, it's very hard to justify it based on that amount of revenue alone. We really need to get to that fault-tolerant achievement to justify this enormous effort globally and in terms of the investment. So, you know, we heard a couple of talks about IBM's progress. We had Han He talking about her work in that area and the challenges. In fact, Han He talked about trying to move away from this challenge of all of the cabling required. So this is a picture released by IBM when they announced their 100 qubit, just slightly above 100 qubit system recently. At the bottom of the dilution refrigerator in the metal box is where the superconducting chip is with that 100 or so qubits, but you see all of the cabling that's required for the input and output. And we've also heard, I mean, the last panel spoke very eloquently about the challenges of networking large numbers of cryogenic systems together. We heard from Jeremy O'Brien, gave a fantastic talk yesterday, very exciting to see what SQA Quantum is doing and their vision. And part of the challenges there are networking all of these cryogenic systems to make very, very large systems. So it appears that most of the implementations around the world at the moment being explored are looking at quantum computers that are going to look like very, very large physical systems, potentially taking up a significant fraction of a building. So with Diraq, our focus is on the opposite, to try to get a quantum computer looking like a traditional computer. Let's get something that is actually a compact unit that doesn't require half a power station to keep it running. So Jeremy yesterday talked about creating a facility equivalent in any energy consumption to SLAC, the Stanford Linear Accelerator. And look, if ultimately that's the only way to make a quantum computer, that's a justifiable goal. I agree with Jeremy. But I think that we can do it better. I think we can do it cheaper. I think that we can do it in a way that's much more portable, for more applications and more users to really truly untap that market, and our view is that silicon manufacturing is the way to go. So one thing I very much agree with Jeremy and SQA Quantum about is that ultimately to get to large numbers of qubits, we need remarkable engineering reproducibility. So, you know, we take for granted now, every day we walk around with a mobile phone or with our laptop, that the chips in there have got billions of transistors, and all of those transistors have to operate perfectly within very strict tolerances, okay? That has taken trillions of dollars and decades, over 50 years of development to get to that level of reliability and reproducibility. Okay, that is the level of reproducibility we are going to need. Now, SQA Quantum have taken the approach of using CMOS manufacturing to make waveguides, okay? And that's their focus on getting that reproducibility. Our focus is to modify silicon transistors, I'm about to show you, and operate those as qubits. And with that, as you can see on this chart, we can get at least 1 billion qubits on a single processor chip. So the comparisons of the numbers of qubits per module there, which are well below 1 million, are taken off publicly available information based on the existing size of qubits of the different technologies. So all of those technologies are having to look at network systems, as we've heard from many of the speakers. We want to move away from that and have a single module, a single chip in one cryogenic cooling system, and I'll talk more about that in a moment. So, as I've said, our concern at the moment is that most companies are focusing on enormous quantum computing processes that begin to, bring up reminders of the first computers in the 1950s. So those computers were based on vacuum tubes, and ENIAC was an amazing achievement. But when it was turned on, the lights in the town used to dim because it was sucking so much power out of the power station, and it had less processing power than a pocket calculator in the 1970s. So the only way we've got to where we are today in the information age is because of the integration that is possible on a silicon chip. Okay, that is how our modern world has worked. And I personally believe that the integrated circuit and the transistor are mankind's most important inventions up to this point that's progressed mankind immeasurably. And it's taken a huge amount of effort to get that reproducibility, to get to that stage. So let me now tell you a little bit about the qubits that we work with at Diraq. So the image at the top is a cartoon of a standard silicon transistor, so-called metal oxide semiconductor field effect transistor, or MOSFET. The gate at the top, coloured grey, is a metallically operating electrode, highly conductive. When you put a positive voltage on it, it draws negatively charged electrons into that region underneath it called the channel, and it connects to other contacts called the source and the drain, the source of electrons and the drain of electrons. And when that voltage is positive, typically around 1 volt or less on modern transistors, it draws the electrons in and it turns the transistor on. If you make that voltage 0 or negative, you push the electrons away and you turn the transistor off. That's the way a transistor works as a digital switch and enables all of modern conventional information processing. What we showed within our team at UNSW, where Diraq span out from in May last year, was that we could reduce the number of electrons in that transistor channel down to just 1 or a handful. We can encode information on the spin or magnetic moment of the electron. We can write information with high fidelity, and we can read it out with high fidelity. And we did that in 2014. And in 2015, we showed that we could put 2 of these devices next to each other and operate 2-qubit logic. We've also shown and designed a variety of different architectures, beginning back in 2015 and published in 2017, full-scale architectures for making millions of qubits, including all of the word and bit addressing that's required to address those, and the electronics to pulse and control. So our focus is making qubits using the standard manufacturing technologies. We don't need to make any changes to these process manufacturing lines inside Tier 1 foundries. Okay? And at the moment, we're working with foundries all around the world to find the ways to most efficiently make our qubits in their foundries using all that same tooling with simple modifications of their process steps, but not without changing materials. And we're very, very close to results on that, which I'll talk about our roadmap in just a little while. But the important thing to take away is that our qubits are just modified silicon transistors, same materials, same manufacturing. And because of that, we're confident that we're going to be able to get the same levels of reproducibility and engineering controls that we're convinced are going to be required for fault-tolerant quantum computing. So this just hasn't been a dream or an imagination overnight. It's taken many, many years, and I want to again acknowledge the long-term important support from the Australian government, from the New South Wales government over many, many years, the investments in the fundamental science which have allowed this technology to become possible here in Australia and indeed right here in Sydney. And this chart shows around just over 10 years of developments going back to 2000 within our team at UNSW as we bit by bit address some of the key challenges. Just highlighting a couple, you can see at the bottom left in 2007, this was a really, really important result where we showed that we could take a modified MOSFET transistor and operate it as what is called a single electron transistor, where we have exquisite control of the individual electrons in the device. And indeed, that was the first demonstration ever in a MOSFET device that one could make useful so-called quantum dots or single electron transistors. And up until that point, most people in the community, I would say 99 or more percent, believed that it was going to be impossible to make quantum devices out of MOS technology and CMOS. So we proved them wrong at that time. And after that, used those transistors. You can see a paper there in 2010 done with my very close colleague, Andrea Morello, who we were entertained by last night, where we demonstrated the first readout of a single spin. And the readout device was one of those MOS transistors. The spin was bound to a phosphorus atom. So at the time, I was working on the approach that Michelle talked about a moment ago at SQC, with the idea of using single phosphorus atoms to combine those qubits. And indeed, with Andrea, in the following 2 to 3 years, and also a brilliant PhD student at the time, now Associate Professor Jared Pla, demonstrated the first operation of qubits on those atoms in 2012 and 2013, using the MOS devices for the readout technology. But around about that time, I was beginning to realise that those quantum dots could actually be extremely good qubits in their own right. And so in 2013, some work led by, who was then a PhD student, Henry Yang, who's in the audience. Henry, now our head of quantum control at Diraq, showed that it was possible to reduce those down to just one electron and to read out the spin accurately for the first time. And that then opened up the pathway in 2014 for this really crucial breakthrough, which was our first ever quantum bit based on a quantum dot. So using standard MOS technology, standard lithography of patterning and manufacture, using our clean rooms at UNSW of the Australian National Fabrication Facility, we were able to demonstrate a qubit, and the very first control fidelity that we ever measured on one of those qubits was 99.6%. Okay? So that result, and the result the following year published in Nature in 2015, you can see below, where we demonstrated the first 2-qubit gate. This led a whole range of research groups and companies to start to look, including Intel, to start looking at MOS qubits as a pathway for quantum computing. So since that time, our team have been pushing on the technology, exploring a whole range of the fundamental physics concepts that are required to make this qubit package a viable qubit for quantum computing. So pushed the fidelities up to 99.96 in 2019. Did the first fidelity measurements on 2-qubit gates in 2019. You can see the papers there. And importantly, in 2020, another great piece of work by Henry Yang from our team showed it was possible to operate these qubits at 1 Kelvin, while maintaining high fidelities. So all of this has been possible, as I've said, from those investments from the Australian, New South Wales government, but also importantly from our partners in the United States. So we've been funded for over 20 years from the US Army Research Office. $30 million have gone into the programs that have made this possible with our silicon MOS qubits, and we greatly appreciate that relationship. It's a very important one. There's no question that quantum computing is a strategic technology. It will ultimately be a dual-use technology, and particularly in troubling times like this, it's very, very important that we work with our close allies like the United States in order to develop this technology in full partnership, and that relationship has been crucial and continues to be crucial for us. So let me now just talk about some of the key advantages that we see. The left I've already talked about, the CMOS manufacture, but also a range of other advantages of the silicon CMOS approach from the perspective of scalability. So I want to show here some work by another lab. This is actually from Intel research, a group of Jim Clark in the US, where in their Intel 300mm wafer foundry, they demonstrated a qubit based on our technology using their manufacturing line, and the fidelity in their first attempt was 99.1%. Okay? I should emphasize that they're not using some of the more sophisticated control techniques that we use within our group, but I'm sure that, I think in more recent work they've been pushing that up higher, and there's absolutely no question that there are no fundamental impediments to making these qubits and making them operate well in a foundry environment. In fact, since that, as well as that, other foundries, including Leti in France and IMEC in Belgium, have also demonstrated CMOS-based qubits using this technology. Another one of the really key, important advantages of CMOS qubits in our mind is their compatibility with standard CMOS electronics. So we've heard now the problem of the cabling, connecting large numbers of qubits. As you see on the left, some of the cabling required for Google's Sycamore chip with 53 qubits. And on the right is a paper from David Riley's team at Microsoft Research, where they demonstrated a standard CMOS chip operating to control, in this case, gallium arsenide qubits. But the important point is they operated this CMOS chip at 100 millikelvin and were able to maintain the power dissipation even at 100 millikelvin. Now, that's going to get challenging when we go up to thousands and indeed millions of qubits, but fortunately, if we simply move the control electronics up to the 1 Kelvin stage and sit the qubits there as well, where we have also very high fidelities, it's possible in one module at around 1 Kelvin to control many millions of qubits using CMOS electronics. And I really think that we are amazingly fortunate here in Australia and indeed in Sydney to have a group like David's. And of course there are a number of other groups around the world also exploring CMOS cryogenic control. So our aim, as you can see on the right there, is to have an integrated module with the CMOS electronics next to the qubit chip. I should mention that one of the advantages of using CMOS qubits is on the same chip we can also integrate quite a bit of control electronics as well in order to address the qubits, because with millions of qubits we can't have millions of wires coming out, we must have multiplexing. But because we can use standard CMOS transistors integrated with our qubits, because we're using the same manufacturing process flow, we're able to do this. So this is an absolutely crucial advantage. One of the other big challenges that many qubit platforms face, not all, but certainly superconducting qubits and a number of others, is the fact that qubits generally each operate at a slightly different control frequency. Indeed, that's typically the way that you get addressing between them. You use different frequencies, generally in the microwaves, for example, for superconducting qubits and for spin qubits. And this becomes a real challenge of frequency crowding. How can you have a million different frequencies controlling a chip? So the way that we have been developing to get around this has actually come from a brilliant idea. Again, Jared Pla, as I mentioned, I don't know if Jared's in the audience, I haven't seen him in the last day or so. Jared is a now associate professor at UNSW, and he came up with a brilliant idea of using what's called a paraelectric material, which has an extremely high dielectric constant at low temperature. and using that to confine a magnetic field and create a resonator that can produce a very large AC magnetic field, but spread across millimeters effectively. And so the idea here is that with this chip, which is we've now demonstrated in the laboratory with our team, together with Jared's team, shown that it's possible to control up to millions of qubits. Obviously, in our experiments at the moment, we're just controlling 1 and 2 qubits, but the basic principle applies. And this global control is going to be very, very important to be able to massively simplify the electronics required to control millions of qubits. So if you're asking then how do you address the individual qubits using standard voltage pulsing, just like standard word and bit addressing. But essentially the clock is being provided by this continuously rotating microwave field. So just to finish up, and I do want to make sure I leave time for questions, I won't be naughty, Bernie. I just want to talk a little bit about the technology roadmap that we have at Diraq. And so this is a roadmap spreading over 10 years. As I mentioned, we only launched in May last year. And our first phase, we're looking to complete within 3 years. Locally at UNSW, we're going to keep pushing our qubit device fabrication to where we think is possible in a university fabrication environment. Now, our qubits are very small and it's very difficult to get acceptable yields in a university environment. But we're confident that we can get that up to about 9 or 10, and that's very important both to get our first systems out available on the cloud for people to start trialling the use of silicon qubits, but also we learn an enormous amount as we operate these qubits, as we've done for the last decade. But importantly, in parallel, we're going to be developing Foundry devices. I'll talk a little bit more about that in a second, but I just want to show people, to give you a visualization of what these qubits actually look like. These are the qubits made in our fabrication facility at UNSW, not in a foundry. You can see here a device that has space for 4 qubits, in this case in just a simple linear array. The devices at either end are the so-called single electron transistors, all MOS technology that are used to read out the spins. And the material that we use is silicon-28. It's isotopically enriched. It removes the silicon-29 isotopes that have a nuclear spin. Fortunately, it's possible to buy wafers of this stuff, where you simply grow a thin epi layer that can be a few tens of nanometers thick. It's worth noting that most electronics in modern day CMOS is all happening up in just the first, tens of nanometers of the chip. The rest is really just holding the chip together. Up on the top right there, we show some data where we're operating 4 qubits on this device at the moment. And so we're pretty confident that we're going to be able to hit that local 10 qubit capability, 9 to 10 qubits within the next 2.5 years. But I mean, if that's all there was, if it was really just being done in a university fab, then there really wouldn't be any justification for a company. We are, at this moment, partnering with Foundries. I'm afraid I can't say who they are due to confidentiality agreements and reasons, but a number of foundries to manufacture our devices in processes that are completely compatible with standard transistors, which allows us to integrate those standard transistors with our qubits to provide the control and multiplexing necessary. So forgive me on phase 2 there for the rather cryptic numbering that I'm targeting. So we're definitely promising more than 256 qubits, but I can't tell you exactly how many at the moment. We might choose to release those numbers perhaps in a year or so, but they are substantial. And to give you a clue, in phase 3, which we're planning to move into in around 6 years from now, we are planning to have capabilities for fault tolerance. Okay, so we will be releasing more information in our roadmap in due course. So just to leave you with a visualization of what we're looking to do, we're trying to take the standard CMOS transistors, so here's a transistor operating with the electrons flowing, reducing them to 1 electron or a small handful, encoding the information on the spin or magnetic moment, manipulating them with a global field to control individual 1 qubit gates, and then interact them through electron-electron spin exchange, and then ultimately get them integrated using standard CMOS manufacturing. And with that, and as I've shown you with the integration of cryo-CMOS control electronics, we're confident we can put all of this in a single cryostat that can be mobile, that can ultimately be the most powerful in terms of numbers of qubits, and because of the fact we're just using one cryogenic unit, way cheaper per qubit and per qubit operation than any competing technologies. And, you know, aside from all of the developments on the hardware, we're also in the process now of building up a quantum software team and quantum algorithms team, and stay tuned, hopefully, for announcements in the coming months. We'll be able to say more about that. You know, building up the full stack. I think Michelle was talking about it, and you know, and many others have talked about the need for quantum computing companies. We must have the capabilities right across the stack in order to partner with our end users and to make sure that we're solving the specific architectural challenges that we need in order to hit fault tolerance for useful problems as soon as we possibly can. So just to finish, I really want to highlight the amazing team that we have within Diraq that's been built up over very many years, really outstanding people, and many of them here from our technical leads are in the audience. At the moment, we have 17 people in the company. We're looking to grow that very rapidly. We're still in capital raising phase at the moment. So if anyone fancies checking me out the back with a checkbook, no problem. Very happy to talk to you. And in addition to our team, we also collaborate with world-leading scientists, both at UNSW, Andrea Murillo and Gerard Pla, but all around the world, in particular with HRL Laboratories in the US, who have been a long-term partner for us. We also have an amazing board. Electus Capital, part of the ICM group, were our foundation investor, been very, very helpful in helping us to steer and guide the company, to build the team, and very, very honoured to have an amazing chairman in Bill Jeffrey. Bill is here in the audience today, so please grab Bill. If people don't know, Bill was the director of NIST for many years as they were bringing up the ion track programs. He then moved to HRL Labs, which was the old Hughes research labs in the Howard Hughes days, but is these days a major defence contractor developing electronics for US defence, and then moved to Stanford Research Institute as their CEO and director for many years. But we're amazingly honoured to have Bill as chairman, and the fact that we have Bill there based in the US is very, very important from our global strategy, as you can imagine. So look, with that, I'd like to thank you for your time. I think I've left a few minutes left for some questions, so thank you very much.
Thanks, Andrew. A really exciting talk following on from hearing about all the challenges and different approaches in our initial panel, and just focusing in on one approach that clearly you have great belief will really get us to fault tolerance in 6 years. Is that what I saw on that last slide?
We're looking to have the first processor chips that have the number of qubits required to get that. I'm not promising full fault tolerant algorithms in 6 years, but I am promising that by the end of a decade.
So let's all meet back here.
Absolutely.
10, shall we?
You
Yeah.
can shoot me at the time.
I would love that. Also, thanks for picking me up on what was so obvious, because I was being so excited about it on the first day. It's the whole supply chain is where there's opportunities for Australia. So I think you did a very nice way of saying to me, it's the stacked supply chain, stupid. So thank you. Yeah, I really appreciate it. All right, questions. So any live in the audience? Oh, I believe that we have we have a question right down here at the front. Honey from IBM.
I asked too many questions now that everyone remembers where I'm from. So it was an excellent talk, and then it was amazing also to see, you know, the whole stack of the fabrications. So I have like one comment and one question. So maybe my first comment is maybe my view is the isotopically pure silicon is also the realm of the outside of the typical CMOS fabrication that you absolutely need for your stack. So that's why, in some level, I think in the future, we don't know how many of those will be needed to really build up to billion qubits. So I mean that was the comment that I was trying to make in the panel session, that we may need to see the future of fabrications and materials. So that's the one comment. And my question is at the level of the billion qubits, there will be a crosstalks I know crosstalk is a big issue for superconducting qubits, but I'm sure it'll be the issue for quantum spin qubits from the chips to electronics. So do you have any like mitigation plans for your crosstalk?
Yeah. So in fact, I mean, I didn't have time to go obviously into the full technical details of the global control approach, but we do have a number of papers on it, and I encourage people to take a look at those, please. Quite a significant stack now of papers. So actually one of the main goals of the global control approach is in fact to move away from crosstalk, because in this situation, because we're only using one driving frequency, effectively there's no crosstalk of the microwave signals because that's flooding all of the qubits. So the only prospect then for crosstalk is between the actual voltages on the gates, you know, with adjacent qubits. And we've done quite a bit of modelling about the amount of stray electric fields, and we're very confident that we can keep that crosstalk down to acceptable levels in order to keep the fidelities high, even as we scale. Can I just come back to the silicon 28 and mention that I showed you that result from Intel? That was done on silicon 28 in their 300mm wafer foundry, and there's now a number of foundries. I mean, let me just explain. All it involves so one of those big tools is an epitaxy tool. You take out the bottle of natural silane and you replace it with a bottle of silane 28. That's the full engineering work required to change. Thank you.
How many papers did you get out of that?
Out of the global control, we've got about 5 papers out there at the moment.
Because I know that the Kohei was working with Intel to implement that process. So, you know, but yeah. So.
Fantastic. And before we go to our next question from the room, there's a very popular one here, which I also want to hear. How much of Diraq's production and manufacturing will happen in Australia? Which I think is a nice way of asking which foundries. And will you keep the majority of your operations and people in Australia, or will you move overseas?
So we're intending to keep our headquarters here permanently. I mean, our intention is to stay here in Sydney. We want to build a global quantum computing company here in Australia, based in Sydney. We intend to do as much of the assembly of the systems, and certainly the majority of the R&D based here in Australia. The chip manufacture, because we need Tier 1 foundries, and if people aren't familiar, a Tier 1 foundry starting price is around about $10 billion US and up. Okay, so we don't have any here at the moment, and so that's why we're working with global providers in secure environments, I should mention. But as I've already said, there's so much assembly, development, components that need to be developed, and we don't intend just to have all of that here in Australia with Diraq, but we can see lots of other companies springing up to supply parts of that supply chain here in Australia. So I see an enormous amount of manufacturing happening here.
Fantastic.
But I do want to say that we don't intend to have all our operations in Australia. We're definitely, there will be components in the US, in Europe and so on, potentially Singapore, etc.
Global company, you mentioned that, yeah. And down the back.
Really awesome talk, Andrew. Jeremy O'Brien from SQA Quantum. So that's the quick comment. Really compelling vision that you've painted there. And quick clarification. Yesterday, I said that we're interested in using cryogenic cooling power of one of the bits of SLAC, not the electrical power of the entirety of SLAC, which is a pretty important clarification.
Sorry, Jeremy. I'm
Thanks,
sorry
Jeremy.
to misquote you, mate. No.
What did you think of that video at the end, though, Jeremy? That was up on par with yours, I think.
It totally is, yeah.
Yeah, good. Nice work. So any other in the room? We've got plenty coming through here. So what will be the range of frequency, megahertz, gigahertz, that these qubits will need to be operated at for 2 qubit interactions, given spin qubit coherence times? What challenges do you face in bumping up the operating frequency, and what are some solutions you hope to implement?
Yeah, so frequencies. So we're looking to operate our qubits in a DC magnetic field, which is around about between 0.1 Tesla and 1 Tesla. That sets the frequency of a spin qubit, so it's set in the gigahertz range. We're looking at operational microwave frequencies between 5 gigahertz, potentially up to a couple of tens of gigahertz, okay? Switching frequencies that we're looking to operate with are in the, let's say, tens to hundreds of nanoseconds. Okay.
Okay, I understand those words. I don't know the value of it.
The person who asked the question
yeah,
obviously
they will
doesn't
know.
want
All
to
right.
know it. Okay.
Another question from the room? Yes? Thanks.
Hi, this is Farina from CSIRO. I actually want to ask that how you are dealing with the entanglement between the qubits and how you're dealing the spin of the entangled qubits.
Okay, so well, the entanglement between the qubits is provided by Heisenberg electron-electron exchange. So it's actually one of the reasons that we need tier 1 manufacturing, because we need the qubits close enough together. So we have to get them to around about 50, 60 sort of nanometers apart in order to have sufficient exchange interaction. And so essentially the entanglement's made possible by the direction of the spin on one affects the phase of the other. And so you can have a controlled phase gate. You can also do swap gates. There are some benefits sometimes to doing swaps for certain process that we use. And so that's how you entanglement. I'm not sure I picked up the second part of your question.
As you showed also a slide, where the guy has, showed how we can do the spin-off a qubit, and how you can do the number of qubits and you can do their spins. So when we talk about the entanglement, we say that now the both qubits are behaving similar.
I understand the question.
And the other thing is that are you doing maximum 2 qubits entanglement, or what is the maximum qubits that you can entangle?
I understand what you're asking. Okay, so in that animation, we were only showing the manipulation of the single qubit gates. We weren't showing the 2 qubit manipulations as well. So we have electrodes that sit between the dot electrodes, and those electrodes control the coupling between the qubits. So we can turn on and off exchange by around 6 to 8 orders of magnitude. Okay, so we can turn exchange completely off. And so and to answer, it's pairwise entanglement. We do pairwise and then we build it up. So we have a variety of different architectures, modifications of the surface code that are compatible with the CMOS designs. Hope that answers it.
Okay, we are out of time, but we are going to do a rapid fire because there's some very popular questions here. If Diraq only has a 9-qubit device in 3 years, won't you be far behind others? And if so, how can you catch up?
The whole answer to that is Foundry. So essentially with our Foundry partners, our goal over the next 3 years is to have a secure supply chain, I'm getting there, of high fidelity qubits. Okay, we want to make sure we've got the 1 and 2 qubit gates operating at the fidelities required. The next step, we start ramping up, and the ramp up is massive and fast. Okay, I mean, the point is that the number of qubits that you can fit onto a chip is already in the millions. We're not going straight for millions, I'll say that, but we are going for very large numbers, and we do intend to be past our competitors in much less than a decade.
That smile has appeared a few times today, so I'm feeling like you've got some quiet confidence there that, yeah, okay, good. Excellent talk. Are you currently planning to make your quantum computers, including the first 10-bit iteration, 10-ish bit, available for sale, aside of cloud availability?
Yes, we are looking at providing complete hardware systems that we can install and potentially in different countries around the world, and we may have some news on that at some stage.
Great. Do you believe a special foundry process specific for quantum devices will be necessary to be developed to ensure silicon?
No.
Thank you. That's how rapid fire should work. I'm glad you get it. Thanks, Andrew. I'm afraid that's all we've got time for. Plus, Andre Morello yawned. What does that mean? I feel like he's heard your talk before. Yeah, it was a big night last night. Yeah.
And I missed it.
Yeah, remember the tip, caffeine. Yeah, it's a thing. All right, thank you so much. We've had a stunning morning. It's been really invigorating. You've got morning tea for half an hour, and then we've got our final 2 panels, which are going to be equally spectacular. First up, the Australia's Strengths in Quantum Sensing, sponsored by KPMG, and after that, our final panel for the conference, bringing the research to commercialise. Bridging the research to commercialisation gap. Don't forget, if you haven't already looked at and voted on the posters, please do that now. Last chance. Get to the booths. You want to be talking to these people who are working in the sector. Have a great morning, team. We'll see you back here at 11:30. Thank you. Fantastic.
Thanks, Jeremy.
Cheers. Really beautifully paired.
Sorry I ate into
No,
the
no.
question.